Episode 36, titled 3.3 Troubleshoot Connectivity and Corrupted Data, First Checks That Matter. Troubleshooting is framed as a professional way to protect time and trust when a data task suddenly stops working. When connectivity fails or data arrives corrupted, teams often lose hours chasing the wrong layer, and the final story becomes more emotional than factual. A disciplined first-pass approach keeps the investigation anchored to evidence so the fix is faster and the explanation is credible when others ask what happened. The exam angle is not memorizing specific tools, but recognizing which checks reduce uncertainty fastest and which checks prevent repeating the same mistake next time. The aim is to build a calm sequence that works whether the failure is a blocked connection, a misconfigured endpoint, or a dataset that changed shape without warning. The first practical move is confirming scope by reproducing the issue reliably, because a non-reproducible problem is not a single problem, it is a shifting target. Reproduction means identifying the smallest, repeatable scenario where the failure appears, such as a specific data source, a specific time window, or a specific environment, while noting whether the problem is constant or intermittent. Intermittent failures often point toward network instability, throttling, transient service errors, or timeouts, while constant failures often point toward configuration, credentials, or a structural mismatch. Scope also includes confirming what broken means, because a complete inability to connect is different from a connection that succeeds but returns partial or malformed results. Once the issue is reproduced consistently, every later check becomes more meaningful because changes can be judged against a stable baseline of failure. Credentials, permissions, and account lockouts are worth checking early because they are common, fast to validate, and frequently misinterpreted as network problems. A credential issue can look like a connectivity problem when the visible symptom is simply access denied or repeated authentication failure without a clear explanation. Permissions can also change silently when roles are updated, service accounts expire, or a system is migrated, leaving an integration intact in name but broken in practice. Lockouts are particularly tricky because repeated retries can trigger security controls, so the failure can escalate from wrong password into account locked, and the second condition persists even after the right credentials are restored. In a professional troubleshooting flow, identity and authorization checks come early because they resolve a large fraction of incidents quickly and they prevent wasted time debugging routes and firewalls when the real issue is access control. Network basics are the next layer, and it helps to keep them conceptual and simple rather than jumping into deep complexity too soon. Name resolution is a frequent culprit, so domain name system, DNS, should be treated as a first-class dependency rather than an invisible assumption. When DNS is wrong, a connection may fail outright, connect to the wrong destination, or behave inconsistently across environments depending on how names are resolved. Routes and basic reachability also matter, because a service can be healthy but unreachable from a particular network segment due to routing rules, segmentation, or a change in where the service is hosted. Firewalls can block traffic in ways that look like the service is down, so early checks should confirm whether packets can reach the destination and whether the path is allowed for the relevant protocol and port. After the basic path is considered, verifying endpoint details reduces the chance of arguing about the wrong target. Endpoint Uniform Resource Locator, URL, values can drift when services move, versions change, or a team switches from a test endpoint to a production endpoint without updating dependencies consistently. Ports matter because a service may be available on one port but not another, and a change from HTTP to HTTPS can introduce transport layer security requirements that behave like a sudden outage when certificates or policies do not align. Service availability also includes upstream health, such as whether a gateway, proxy, or load balancer is functioning, because a failure there can block access even if the backend service is healthy. A good troubleshooting habit is to confirm the endpoint identity, the expected protocol, and the expected port as factual statements rather than assumptions that must be correct because it worked last month. Error messages should be inspected for hints, not blame, because blame-seeking wastes time and tends to shut down cooperation. An error message often indicates the layer where the failure occurred, such as authentication, authorization, name resolution, connection timeout, or data parsing, and that clue narrows the search space dramatically. Even a vague message can still be useful when paired with context, like what changed recently, when the failure began, and whether the error is consistent across attempts. The important discipline is to treat error text as a symptom description, not as a verdict, because some systems wrap underlying errors and can mislead if taken literally. A calm reading of the message, combined with reproduction steps and environment details, turns the message into a structured lead, rather than a trigger for finger-pointing. Connectivity is only half the story, because sometimes the connection succeeds and the real failure is corrupted data that breaks downstream logic. Corruption can appear as garbled text, replacement characters, or unreadable symbols that often point to encoding mismatches between systems that use different character sets. Truncation is another classic sign, where values are cut off due to field length limits, schema mismatches, or serialization rules that silently drop content beyond a threshold. Corruption can also show up as missing delimiters, broken quoting, or shifted columns in delimited files, which can turn a clean table into misaligned fields that still load but carry wrong meaning. The professional instinct is to treat "we got data but it looks wrong" as a high-risk condition, because incorrect data can silently drive incorrect conclusions while still producing valid-looking computations. Row counts and hashes are simple but powerful methods for detecting unexpected changes because they provide objective signals that something changed even when the content is too large to inspect manually. A sudden drop or spike in row count can indicate missing partitions, duplicate ingestion, filter drift, or a source system change that altered what records are emitted. Hashes, used carefully, can confirm whether a dataset is identical, partially changed, or unexpectedly different between two runs, which helps separate the pipeline changed from the input changed. When counts and hashes are compared across stages, they also reveal where the change was introduced, such as during extraction, during transformation, or during a merge that silently filtered rows due to key mismatches. This kind of evidence protects trust because it gives a clear basis for saying, "the data differed before our logic touched it," or "the data changed after a particular step." A pipeline failure scenario helps make the first checks feel practical rather than abstract, because pipelines fail in predictable patterns that map to the same layers repeatedly. Imagine a nightly load that usually completes, but today it fails at the extraction step with a timeout, and then on retry it succeeds but produces fewer rows and unusually long text fields that appear truncated. In that scenario, the first pass should separate "can the pipeline reach the source" from "is the data being returned the same as usual," because those are different questions with different fixes. The timeout suggests a connectivity or service availability issue, while the row drop and truncation suggest a content or schema issue, possibly caused by a source change, an encoding change, or a new field exceeding expected length. A disciplined approach treats the scenario as two linked problems, until evidence shows they share a root cause, because bundling them too early can lead to the wrong conclusion. Isolation is the skill of swapping one variable at a time so the investigation produces signal rather than confusion. One variable might be environment, such as comparing a development run to a production run. Or it might be source endpoint, such as testing the same request against an alternate region or alternate replica if one exists. Another variable might be time window, such as requesting a smaller slice to see whether failure is tied to a specific partition or whether corruption appears only after a certain date. Isolation can also mean removing one transformation step temporarily to see whether the corruption is introduced during parsing or whether it already exists in the raw input. The key is restraint, because changing multiple variables at once can make the system appear to improve or worsen without revealing which change mattered, and that wastes time when stakes are high. Timestamps and environment details should be captured early because they turn troubleshooting from a memory exercise into an evidence trail that supports later review. Time matters because network issues, service outages, key rotations, and source changes often occur at specific moments, and without exact timing, it becomes hard to correlate symptoms with known events. Environment details matter because the same pipeline can behave differently based on region, network segment, role permissions, endpoint configuration, and even library versions that affect parsing and encoding behavior. Recording these details also helps separate intermittent issues from deterministic ones, because a repeating failure at the same step and same time suggests a scheduled dependency, while scattered failures suggest instability. When a team can describe what happened, where, and when precisely, it becomes much easier to involve the right owners and avoid cycling through generic suggestions. Escalation works best when it carries clear evidence instead of vague descriptions, because specialists can act faster when the symptom is well described and the investigation trail is already structured. Evidence can include the exact error text, the reproduction steps, the time of occurrence, the affected endpoint, the scope of impact, and the observed differences in counts or hashes compared to a known good run. It also helps to include what has already been ruled out, such as confirming that credentials are valid or that name resolution works, because that prevents duplicated effort and shortens time to resolution. Vague statements like, "the pipeline is broken," tend to trigger back-and-forth questions that delay action, while a concise, evidence-based summary enables immediate routing to the correct team, whether that is identity, network, platform, or source system ownership. In high-trust environments, escalation is not an admission of failure, it is part of responsible operations. A repeatable first 5 checks routine can be summarized as a mental sequence that moves from fastest, most common causes to deeper structural causes while preserving evidence at each step. The sequence begins with confirming reproduction and narrowing scope so the problem is stable enough to measure. Then it checks access conditions like credentials, permissions, and lockouts because those fail often and are quick to validate. It then validates basic network dependencies, including domain name system, DNS, routes, and firewall allowances, because these determine whether the service can be reached at all. Next, it verifies the endpoint identity, protocol, port, and service availability, because an incorrect target or mismatched transport expectation creates failures that mimic outages. Finally, it looks for corruption signals and compares counts and hashes to detect unexpected content changes, because a successful connection can still produce unusable or untrustworthy data. The conclusion of episode 36 sets one troubleshooting log habit to start immediately, because the log is what converts a stressful incident into a reusable learning asset. The habit is to capture the first observed time, the environment, the exact symptom, and one objective measurement, such as a row count difference or a hash mismatch, even before a fix is found. This habit makes future incidents faster to resolve because the same baseline questions are answered automatically rather than reconstructed from memory. It also improves communication because stakeholders receive a clear story of what failed, what was checked, and what evidence supports the conclusion, which preserves trust even when the issue is not yet fully resolved. Over time, a simple log habit turns troubleshooting from reactive scrambling into a controlled process that protects both delivery timelines and analytical credibility. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.